All right, let's talk about the microscopic world that, believe it or not, powers pretty much everything in your digital life. Your phone, the internet, all of it. We're going to uncover the silent engine behind this whole revolution. Silicon.
So take a second and think about that. Your phone, your car, the entire internet. They seem like completely different things, right? But they all share this one secret ingredient, a kind of common ancestor, if you think about it.
And here it is. It sounds like science fiction, but it's true. At the very heart of all this tech is basically just purified sand, silicon, that we figured out how to control. We literally taught a rock how to process information, turning it into the most powerful tool humanity has ever built. Okay, let's get into how this actually works. The key to this entire technological marvel is something called a semiconductor. It's the real unsung hero here, making everything from your laptop to your smart toaster possible. So what is a semiconductor? Well, it's a material that isn't quite a conductor, something that lets electricity flow freely, and it's not quite an insulator, which blocks electricity completely. It lives somewhere in the middle. But the magic, the really important part, is that last bit. Its conductivity can be controlled, and that is everything. Let's put it this way. Think of a copper wire. That's a conductor. It's like a wide-open 8-lane highway for electricity. No problem. An insulator, like rubber, that's a solid brick wall. Nothing's getting through. But a semiconductor like silicon, now that's the interesting one. It's like a gate that we can open, we can close, and we can even decide how much to open it. That control is the whole game. But here's the catch. Pure silicon all by itself isn't actually that useful. It's like a blank canvas, It has all this amazing potential, but it's not a masterpiece just yet. Let's look at why that is. You see, in its pure crystal form, every silicon atom is locked up tight with its neighbors. The electrons are all stuck in these strong bonds. They have no freedom to move around, which means no electrical current can flow. For all practical purposes, it's just an insulator. Sure, you can heat it up and break a few bonds, but the current you get is so tiny it's basically useless. We need a way to change this. So, how do we get control? How do we turn this boring insulator into our amazing, controllable gate? Well, this is where the genius comes in. The answer is a brilliant process that's honestly more like a recipe in a cookbook than some feat of heavy engineering. It's a process called doping. And no, not that kind. In materials science, doping just means we intentionally add a tiny, tiny amount of a different element, an impurity, into that pure silicon. We're just sprinkling something extra in there. And this one simple trick completely transforms how the silicon behaves. And this gives us our two different flavors of silicon. If we add an element like phosphorus, which has one more electron in its outer shell than silicon does, we end up with an extra, free-roaming electron. Since electrons have a negative charge, we call this N-type silicon. But what if we add something like boron, which has one less electron? Well, that creates a gap, a hole where an electron should be. This hole acts like a positive charge, so we call this P-type silicon. So now we have our two types of silicon, N-type, which is full of extra electrons, and P-type, which is full of these holes. On their own, they're interesting, but the real world-changing breakthrough happens when you put them right next to each other. This combination creates the single most important structure in all of electronics. The second you join the P-type and N-type silicon, something really cool happens. The free electrons from the N side immediately see all those empty holes on the P side and rush over to fill them. But this only happens right at the border. This little migration creates a barrier in the middle. We call it a depletion zone, where there are no free charges left. And this zone creates its own electric field that acts like a wall, stopping any more electrons from crossing. And this is our controllable gate. Because now we can apply our own voltage. If we apply it in one direction, we call that forward bias, we can push against that barrier, shrink it down, and let current flow right through. Gate open. But if we flip the voltage the other way, reverse bias, we make that barrier even bigger and stronger, blocking almost all current. Gate closed. We've just created a perfect microscopic one-way street for electricity. So we have a microscopic one-way gate. Big deal, right? Well, it's a huge deal. How do we get from this one simple component to the incredibly complex devices that run our world? It turns out this humble little gate is the fundamental Lego brick for
Well, everything. That simple PN junction we just made, that's a diode. It's the most basic one-way valve for electricity. Now, what if you get clever and sandwich 3 layers together, like an NPN sandwich? You create a transistor, which can act as a tiny, ultra-fast switch. The transistor is the real atom of modern computing. And when you figure out how to etch billions of them onto a tiny piece of silicon, you get an integrated circuit, a microchip, the brain inside your phone, your computer, everything. So when you boil it all down, here's the bottom line. Every app you use, every photo you take, every bit of information flying across the internet, it is all possible because we figured out how to create and control billions of these microscopic switches on a tiny slice of rock. That's the secret. And that really just says it all, doesn't it? This technology is so woven into the fabric of our lives that we don't even see it anymore. But it's there, working away in the background, this incredibly powerful, silent engine driving our entire digital world, all built from a simple rock that we taught how to think.